Hello, class. Okay, so we do a problem involving Gauss's law. And let's say we take a charge Q and put it at the corner of a cube with length A. So for specific numbers, let's say Q is minus 8.3 microcoulombs and A is 3 centimeters. Question is, what is the flux through each face of the cube? So there's 6 faces. We want to find the flux through each of the 6. And let me try and draw some electric field lines. So again, this is a cube. We're not going to have this nice symmetry that we have, like for a point charge, if we draw a spherical surface. Let me write down the definition of flux. Yeah, flux through any surface is the integral E dot dA. And we don't even want to think about trying to evaluate this integral over like this face here, for instance. Because the electric field is going to be varying in both direction and magnitude depending on where you are on that face. So that's pretty much out of the question. I mean, it's not impossible, but let's look at Gauss's law. So flux through any closed surface is Q over epsilon naught. And this is good, even if we don't have this nice symmetry, we can use Gauss's law to find the total flux through a closed surface. Now, the problem in this example, the surface we are given does not enclose the charge. The charge is at the corner. And so it's not completely enclosed by the surface. So what we're going to do is let's, well first I want to draw some of these electric field lines. It's kind of hard to draw in, because we have a 3-dimensional cube, but these field lines are radial. But try to imagine the like this face here, like the 3 faces that share a corner. So, should have actually brought a cube. This will be close enough for our cube. So let's say this is a cube. And we place a charge here, like right at this corner. So the electric field lines are radially towards this charge, and so I made this one negative. But if you look at this face here, all the electric field lines on this face are towards this charge. They're all along this surface. Same with the bottom surface, or this surface on the side. The electric field lines are all just along the surface. So the flux through, maybe we should name these. Probably shouldn't have drawn this picture. Let me just redraw it. So here's our charge. So we've got this surface here. We'll just kind of, I'll use a different color to outline them. This surface here, this one here, and this bottom surface. Hopefully that picture makes some sense. The flux through all these blue surfaces, like this one, the bottom one, and that side one, those are the ones that are touching the charge. The flux through, I'll just call those blue surfaces. The flux through each of those is 0. But what about the other three faces? Well, from symmetry, it's a cube. We can say that the flux is going to be the same through each of those faces. So whatever it is, it has to be the same. But the problem is, how do we use Gauss's law in this case if we're not completely enclosing the surface, our charge? And one thing we can do, imagine that we had 8 cubes. So, let's say this is our charge. Let's look at it like a top view. So like say this is x, y, and z is coming out of the board. So our cube would look something like this. If we're looking down, our cube is going to look like this. Color is dead. So it's that one. Okay, that's weird. So again, this is our cube just looking down. So imagine that this is just like above the z, like the xy plane. And so that's this cube here. What if we draw 3 more here? So we have 4 cubes above the plane and also 4 cubes below this xy plane. Then we have this large cube that completely encloses our charge cube. So we'd have a total of 8 cubes with this charge q right in the center of that. And so let's call the flux through that surface, there's 8 cubes. So the flux through the 8 cubes, that would be q over epsilon naught. And the flux, and because it's symmetric, the charge is right in the middle, they're all cubes. And so by symmetry, the flux through each of these cubes would have to be the same. So the flux through a single cube would be q over 8 epsilon naught. Now there's another way you could look at it, and you could kind of break this charge up. It's at the center. And say if that charge has some volume, it's not just a point charge, it has a small amount of volume, 1/8 of the charge would be in each of these cubes. But either way, same thing. So the flux through this cube is q over 8 epsilon naught. So let's look at that. So the flux through our entire cube and let's plug in the numbers. We have a minus 8.3 coulombs over 10 to the 6. Let's put the 8 down there. So 8 times 10 to the 6, that's q over 8. And then epsilon naught is 8.85 coulomb squared over 10 to the 12th Newton meter squared. So we'll get units of Newton meter squared per coulomb. And that's a flux through this entire cube. So let's see what we get here. Simplify this a little bit. I'm going to take 10 out of here. So I'm going to write 83 I think that should do it. It's going to be kind of close. So basically, I took 10 out of here to write 8.3 is 83. So here's 10 to the 11th over 10 to the 6th. That would be 10 to the 5th power Newton meters squared per coulomb. And I think this should be scientific notation now. So I'm going to check 883 times 8.85. I think I did that wrong. 8 times 8.85 is 70.8. So 83 divided by 70.8. So we have minus 1.17 times 10 to the 5th power Newton meters squared per coulomb. So that's the flux through this entire cube. Now the flux through the blue faces we know is 0. Let's look at the red ones. That would be the other 3. I mean, there's 3 of those. So the flux through the red faces, again, if you add up the flux through all 6 faces, you have to get this. And if you add up the 3 blue ones contribute nothing. And the 3 red ones have to contribute equal amounts to the flux just from symmetry. And so we just divide this by 3. So let's do 1.17 divided by 3. That's 0.39 times 10 to the 5th, or minus 3.9 times 10 to the 4th Newton meters squared per coulomb. Okay, so we found the flux through each of the faces. So that's one problem in Gauss's law. Where it's not simple. You have to think, you have to kind of create a situation that you can solve and then figure out, just from symmetry. And also look at the field lines. Like you can use Gauss's law to find the flux through the entire cube. But again, it's not equal through all 6 faces because the electric field lines are moving along. They're all radial. So like along this face, none of the field lines are passing through that surface. So the flux through 3 of them is 0. And then the other 3 are equal to each other. Okay, so that's one problem in Gauss's law. Do another one, but I'll do that in a separate video.